Okay. Yeah. Okay, let's start today's session. Okay, so welcome everyone to week 2 of this NPTEL. Okay, let me just make it full screen. Sorry. I guess I have to do one more thing. Change the layout. It's okay. Yeah. Okay. So let's start today's session. Let me just check if there is some right. Okay, so welcome everyone to week 2 of our NPTEL PM. Oh, sorry. To our NPTEL PMRF problem solving sessions on this course Electronic Theory of Solids. For people who are new, a brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Solid State and Structure Chemistry Unit SSCU of the Indian Institute of Science ISC Bangalore, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL-PMRF TA for this course, Electronic Theory of Solids. So in the last session, someone asked for my email ID. So here is my email ID. So in case if you want to discuss something, so earlier I guess I have 1 minute. Okay, so this is my email ID as well. akshaymahaja@iec.in. So if you want to send, if you have any doubts, you can send me here as well. But like instead of discussing it on through email, I guess so. I would like to discuss before starting today's session. There is one more thing that I would like to discuss. Let me share this screen. Okay, and let me go to. Okay, 1 minute. Let me just share the entire. Stop sharing. Okay, let me 1 minute. Let me just share again. Stop presenting. Let me share the entire screen. Okay, let me just share the entire screen. Okay, no, I don't share the entire screen. Let me share this. Okay. So, okay. That's 1 minute. So, yeah. So, hopefully, okay. So, hopefully, you can see my screen. So, just quickly, I want to discuss this thing. So, here in this, this is the course website. Alright, and on the course website, there is this new session that has been created, which is problem solving session January 2024. So if you go there and click here, just a minute. Alright, so if you go there and okay, so it is here in this section, problem solving session. If you click here, so there is this link is provided. Click here to view the problem solving session. So if you click here, then okay, let me share this tab. Okay, so if you click on that one, then this so this Google Sheet will come. So in this Google Sheet there will be links for all the recordings of these sessions is provided. So like there is the recording for our previous session. So all these sessions are being recorded and they will be uploaded on YouTube as well. So you can go to these links and find the YouTube channel, and also there is a link for this Google Drive link as well, presentation folder link. So all the problem that I am solving, so all this material that will also be shared on this Google Drive. So you can go to this Google Drive link and get access to all the problems that we will be solving. All right, and if you want to discuss. And one more thing, if you want to if you have any doubts regarding the after the session, if you have any doubts, so one thing would be like you can go to the you can go to this YouTube link. Okay, let me just open. So you can just go to that, like this is for the week 1. So you can just go to this. 1 minute. Share. Alright, so like this is the YouTube video link for the previous session. So you can just go there and ask the doubts in the comment if you want. Okay, or one or other thing. Okay, 1 minute. Let me just share again. Okay, or or we can or you can go to this ask a question, which will open that discussion forum of the course. So you can post your question here as well. Right. Yeah, discussion forum. So you can post your question on this discussion forum as well regarding this session, or I guess regarding the course as well. Yeah. So here also specifically for this session, you can post your question on this discussion forum as well, and yeah, I will try to answer those questions there as well. Or you can ask the whatever the queries you have in the next session as well. Yeah. So the YouTube link. So that 1 minute. Let me just go again. So that is on the course website. So the YouTube video link that is on the course website. So here, you can see. Yeah. So on the course website, there is the new session has been created, which is the problem solving session. Okay. So when you go to the course website, there are like week lecture videos, and with that there is this problem solving session tab is also there. So you can just go there, and there will be this link. Okay, and you just have to click there is link. There is this Google Sheet, and in Google Sheet there is there will be the link for the YouTube links for these sessions, for the recording of these sessions. All right. Okay. Are there any other doubts? Okay. Yeah. So let's start today's session. So this is just like this is just a quick information that I want to provide it. So you can go to that link and watch the videos later, and also access this notes as well. Whatever we discuss, all these problems, that PDF will also be shared with you. Right. So from that tab you can access them. All right. So let's start today's session. So first of all, okay. So first of all, let me just. Alright, so let us first discuss something from week 1. Alright. So so in week 1 there was one derivation that I did, and I did some mistake. So it was there was some mistake in the derivation for the average relative speed. So for the problem of mean free path. So I gave a very, like, this derivation is also not quite correct. This was very crude, you can say, derivation. But let me just discuss it again. Derivation for the average relative speed, right? So this is regarding the mean free path that we discussed in our previous lecture. So there we have this relation that the average of the relative speed for the molecules, that will be equals to root 2 times of v bar, where v bar is basically the average speed of the molecule. So for this, what I had shown is, let's say we have 2 molecules. All right. So this is just a recap of what we did earlier. So we have 2 molecules which are moving in v1 direction, and one is moving in v2 direction. And what we can do is, we can take the v relative as let me just minus of v2, and this will be this is the vector, and let's say this will be our v relative vector. Alright, so this is for the random molecule velocity. These are random molecules velocities. Alright, so this is what we have done. So and we can write our relative velocity as v relative is basically, we can write it as v1 vector minus v2 vector. So from there we can write as v relative. So I am not going to take the square root this time initially. So what we can do is, okay, this mod of this v relative square, that could be written as v relative dot v relative. These are the velocities, and we can write it as v1 vector minus v2 vector dot v1 vector minus v2 vector. We can write it as v1 vector dot v1 vector and 2 times v1 vector dot v2 vector plus v2 vector dot v2 vector. Alright, and this thing, then this could be written as mod of v1 vector whole square minus 2 times v1 vector dot v2 vector plus mod of v2 vector whole square. This will be mod of v relative vector whole square. And let me just write this mod of v mod as v relative. Okay, so I am removing the vector sign. I'm just removing the vector sign. This is the magnitude of this mod of v vector will be v1, and magnitude of v2 vector will be, I'm just representing by v2. So I have v relative square is equals to v1 square minus 2 times v1 vector dot v2 vector plus v2 square. Now take average on both sides. Alright, so we have v relative square mod is equals to v1 square mod minus 2 times v1 vector dot v2 vector mod plus v2 square mod. Alright, and this will be this will be 0. Okay, as I have explained in the last lecture as well. So this will be 0 since since v1 vector and v2 vector are random, and since v1 vector and v2 vector are they are random and uncorrelated. Alright, so they are random and uncorrelated, so that's why this will be 0. So we are left with v relative square average should be equal to v1 square mod plus v2 square mod. Now here so here okay, now so let me just so okay, now here what we see there, we can assume that, okay, here I will take an assumption that assume same speed for all molecules. Alright, so what we can assume that okay, so we earlier we can one assumption which is more correct is that the average velocity of all the molecules, that is going to be like same. That's why we are taking v1 bar to be same as v1 bar equals to v2 bar in the last lecture. But here, since we are taking the average of the square, so if we have the values which are basically same, then the average of the square will be equals to the square of the average. Alright, so if all the v1 values, whatever the values of these molecules are going to be, if we just assume that like the velocities are changing, but this speed is more or less the same, whatever the thermal energy the molecule has, so the speed is more or less going to the same, but this one molecule could have velocities in different directions, but the magnitude will be more or less the same. If I just consider that, then in that case what I can what I'm saying is that, okay, so in that case what I can write is this 1 square bar, I can write it as 1 bar square. Alright, if I'm considering that all molecules they are moving with the same speed, so I'm not saying the same velocity, like the velocities are random, but the magnitude is more or less the same, which will correspond to whatever your thermal energy of the molecule will be, that will depend on the temperature. So we can just assume that it is more or less same. Alright, and that I can say that will be equals to some V bar square. Okay, just someone wants to join. Alright, and similarly V2 square bar, I can write it as V2 bar square, or I can write it as V bar square. Okay, so that is just saying that they are just all have the same similar speed. And similarly we can assume that, and similarly like you can say that this V relative also, that is going to be same. Okay, that is also going to be same. So you can also say that V relative square bar could also be written as this V relative bar, whatever the average will be. So the relative velocities, they are also going to be magnitude wise, they are going to be similar only, because these speeds are also more or less same. So from there you can write, we can write this as V, the average of the average relative velocity square will be equals to average of V1 square, which will be V bar square, and this will be also going to be V bar square. So we will have 2 V bar square equals to V relative bar square. So our average of relative speed, will be equals to root 2 times of average speed of these molecules. Alright, so earlier, yeah, so in the previous lecture what I did was I took the average under the square root, which is wrong. So that could not be right, and that would be right mostly if we go with this assumption. So it's better to, so in this case I didn't take the square root initially, and but then again I have to take into account that the average of these squares of the velocities is going to be equal to the square of the average, and that will happen if if all the magnitudes are constant. Okay, let's say we have like 3 kinds of velocity possible for the molecule 1, and I'm saying that all are of the same magnitude. Okay, like they are in different direction, but they have the same magnitude of speed, almost same we can consider. So I am considering same them to be VVV. So either you take the average, so one will be square of the average, which will be 3 sum of these v's, which will be v plus v divided by 3 whole square, which will be equals to, you can see it will be v square. And if I take the square average, so that will be v square plus v square plus v square divided by 3, that is also going to be v square. Alright, so that's why to show, and so to make sure that this thing is possible, so what I have assumed that all of them, they are moving with same speed only, more or less they are moving, all of them are moving with the same speed. Their velocities might be different, they were moving in different directions, but more or less their speed are same, and that's why I have taken this v1 square bar will be equals to v1 bar square. Right, so this thing is possible. Similarly v2 square bar will be equals to v2 bar square. Alright, and again this derivation is not that correct. You can say that this is very kind of a crude derivation for that thing, but hopefully I guess this is fine now. Okay, alright, okay, so let's move to other problems. So this week's problem. Okay, so first we will solve the 2 remaining problems from the last week. Okay, so because of time constraint we were not able to solve this problem. So let's just solve this problem first, or maybe we will come back to this problem because I have to solve. Okay, so we will solve the 11 and 12 problem from week 1 later. So let's just start with problem number 1 of today's session, and then we will solve those 2 problems in the end, which were left from our previous week. Alright, so let's start with problem number 1 of this week 2. Alright, so our first problem is, okay, first we have to find what is the probability of occupancy of a state of energy 0.05 electron volt above the Fermi energy. Alright, so I guess okay, so what is given to us, we have to find the probability of occupancy of a state of energy which is 0.05 electron volt above the Fermi energy, and we have to take the temperature to be 300 Kelvin, and Boltzmann constant is also given to us. Alright, so for this case the probability probability of occupying of occupancy of a state at energy E is given by this priority that it will occupy an energy. So the priority that state will be occupied, okay, occupancy of a state at energy E, that is given by 1 upon exponential of E minus EF by kBT, which is the Fermi distribution basically. So that will give you this probability that a particular state will be occupied or not. Alright, and here E minus EF, so it is written that we are 0.05 electron volt above the Fermi energy. So we have to find that priority that it is above. So E minus EF here is equals to 0.05 electron volt. Alright, so that is our E minus EF. So our probability P of E will be just given by exponential of 0.05 divided by this Kb value is given as 8.625 into 10 to the power. So I am taking this value in electron volt because E minus EF is also given in electron volt. So I am taking this electron volt per Kelvin. So 8.625 10 to the power minus 5, that is electron volt per Kelvin, times 300. Okay, so this will be dimensionless plus 1. Okay, and if you solve this comes as P of E will come as 0.127. Alright, okay, so mainly this is the main thing that you have to remember, that the probability that a particular state is being occupied at energy E, that is given by your Fermi-Dirac distribution. Alright. So let me just okay, if there are no doubts in this one, okay, 1 minute. Is there any doubt or okay? Alright, so let's move to our problem number 2. So the problem number 2 is find the relaxation time for free electrons in copper if the density n of mobile electrons is given to us, which is 8.4 into 10 power minus 28, and the resistivity rho of the copper at room temperature, that is also given to us, okay, 1.7 into 10 minus 8 ohm meter. Okay, so and we have to find the relaxation time. Okay, so for this we will use what we have in the two-day model. So this problem is related to two-day model. So from two-day model, from two-day model, so since we are talking about free electrons in copper, which is a good metal, so two-day model seems to work quite okay for this system. We can write the conductivity. From two-day model we have conductivity is equals to Ne squared tau by m. Alright, okay, where n is our electron density, okay, n is our electron density, E is our electronic charge, tau is our relaxation time, and m is our mass of electron, and this is our conductivity. Okay, and what is given to, so from here we can find that our relaxation time tau is given by sigma m upon Ne square. Alright, and we also know that sigma is equals to 1 by rho, where rho is our resistivity. Okay, so tau will be our relaxation time will be given by rho and m upon rho and E square. Okay, so this is the formula for our relaxation time. Alright, and then we just have to put in the values. So the mass of the electron will be 9.11 into 10 to the power minus 31. Okay, that is given here. Okay, mass of the electron is given here in kg, and all the values they are in SI unit, so you just need to check the units when you solve this kind of numerical problems. Then this is the resistivity, which is 8.4 into 10 to the power 28 times okay, so this is so what is the resistivity? This is not the resistivity, this is the n, okay, n e square rho. Okay, let me just write it in this way, n e square rho. Okay, n e square rho. So n is 8.4 into 10 to the power 8, okay, per meter cube, and the electronic charge 1.6 into 10 to the power minus 19 coulomb O square times the resistivity, which is given as 1.7 into 10 to the power minus 8 ohm meter. Alright, and after putting all this value, if you do the calculation, the relaxation time comes as 2.49 into 10 to the power minus 14 seconds. Alright, 2.49 10 to the power minus 14 seconds. So this was our problem number 2. Alright, so mainly for this problem, you just need to remember that this formula for this problem, like from 2-day model, the conductivity, how conductivity is related to your relaxation time, and the electronic charge, electron density, and also like the sigma is equals to 1 by rho, where rho is your resistivity. Alright, let's go to problem number 3 then. Okay, so the problem is, what is the dimensional formula for the Hall coefficient? Okay, we have to find the dimensional formula for the Hall coefficient. Okay, now we know Hall coefficient is given by, so RH is equals to 1 by n times the charge. Okay, I'm taking a Q here. Sorry. So here I guess in the lecture there is one C, for that is for the unit. So if you have everything in the SI units, then the formula for Hall coefficient is just 1 upon n times the whatever your charge of the carrier is. Okay, what is the charge of your charge carrier, which is mostly for electron it is minus E. So that's why the Hall coefficient will come as comes as minus 1 by Ne. Alright, so it comes as minus 1 by Ne if your Q is equals to minus E. Charge carrier is your electron. Alright, okay, and here, okay, so here the N is equals to number density of charge number density of charge, which is N by B, okay, and Q is the charge. Okay, Q is the charge on your charge carrier. You can just take it as charge. So we have RH is equals to V upon N times Q. Right, and then using elementary dimension analysis, we get, so if you do the dimension analysis, then we can simply get whatever the dimension of your volume is divided by dimension of n, so for Q, and basically there is no there are no dimension for n. Okay, n is just a number, and the dimension of L will be L to the length Q. Okay, length L, and the dimension of charge we know is coulomb. It is basically current times time. That is just ampere times T. So the dimension of your this Hore coefficient, that will be equals to for m it will be 0, for n it will be 3, for a it will be -1, which is for the current ampere, and for time it will be -1. So this will be your answer for the dimension of your Hore coefficient. M0 L cube A inverse dx. Alright. They have just used coulombs. Okay, just a minute. Yeah, I'm not sure. One can. Yeah, I guess one can use if you define, but generally, yeah, I guess generally there is no unit for coulomb. Like we represent for dimension analysis, we represent it. Yeah. Hmm. Yeah, yeah, I guess for the like assignments and the exams, I guess they will be optional, because mostly this question will be in some form of like multiple choice question or something. So I guess you can identify from there, like if the options are written in terms of coulomb, or if in the question it is mentioned that give it in the powers of coulomb, then yeah, I guess you can provide, or you can and if it is like some subjective question, then I guess both the answers are correct. You can provide in this way, or maybe in that coulomb, just giving in the power of coulomb, I guess. But I have not seen. I guess generally it is like current we take A. For current we take A, but yeah. Okay. Alright. So this was our problem number 3. Okay, so yeah, so that depends on the problem. If in the problem, if in the options it is written like in coulombs, or in the question it is mentioned that give the power of in coulombs or something, dimension of coulombs, dimension of charge, then that also could be done. Or in general, it is written like this. Alright, so let's go to problem number 4 now. Okay. So in problem number 4, what we have is the Fermi energy of a matter is 5.51 electron volt. So Fermi energy is given to us, and the average energy of the electron at 0 Kelvin, it is given by, let's say, this average. Then the temperature at which a classical free particle will have this average energy is given. Okay, and it is saying that let's say a classical free particle will have this energy, average energy E. Let's say it will have that energy at some temperature T. So we need to find the average energy E, and also this temperature T for the classical particle, this temperature T for which a classical particle can also have the same energy. Right, the same energy as the average energy of this electron, where the Fermi energy is also provided to us. Alright, so now the average energy, that is, so for this type of question, the average energy first we have to find. So average energy could be written as integration from 0 to infinity, whatever my I will just denote it by E now. This density of states is times the probability that so as we have seen in our first problem, f of E gives us the probability that that a state at that a particular state at energy E that is being that is occupied by some electron. So f of E is that probability. So when we have to find the total energy at some temperature, so this is the formula for if you want to provide at any temperature. This is the total energy basically. So the formula for total energy at if we have to calculate the total energy at any temperature, then we have to integrate. We have to do the integration from 0 to infinity. We will integrate the density of states, how many states we have, times the probability that that state is being occupied at that temperature, which is f of E, times the energy E, and integrated by dE. Okay, and that parameter E. Alright, and this will be divided by, since we are talking about average energy here, so average energy is basically we can take as total energy divided by the number of particles. So that will be just G of E times F of E dE. So average energy is basically just a total energy divided by the number of particles. Okay, this is the total energy divided by the total number of particles, that is your average energy, and it could be and it can be calculated like this. Okay, at any temperature. So this formula will work for any temperature. You just have to put, and the temperature will be in this Fermi-Dirac distribution. Okay, so temperature will define if that state will be occupied or not, and by the density of state, that is providing us whatever the density of those states is at that particular energy. Now now it has asked that the average energy at 0 Kelvin. So at T equals to 0 Kelvin, okay, so we know that F of E, that is given as 1 for energies less than equals to Fermi energy, and it will be 0 for energies greater than the Fermi energy. Alright, so that's why our average energy formula will change to integration from 0 to EF, because above EF, this F of E, our F of E is going to be 0. So this will be just integration of G of E dE divided by 0 to EF G of E dE. Alright, now for now and we are doing it for a matter. So basically our density of state is our density of, we will use the density of state for the 3D case. Okay, this is for a free electron, free average, we can consider free electrons in a matter. So this density of state will be for in a 3D case what we have for the free electrons, which is given by V upon 2 pi square 2m upon h pi square 4 to the power 3 by 2 e to the power 1 by 2. Alright, now you can see that all these terms, okay, all these terms, they are just some constants. Okay, so these are just constant. Under the integration they are going to be constant, and we have this so we will have this constant above and below, both in the numerator and denominator. So these constants are just going to cancel out, so we can just write our average energy as integration from 0 to EF. We'll have e to the power 1 by 2 from this density of state, and the energy E dE divided by integration again 0 to EF e to the power 1 by 2 dE. Alright, and whatever this constant values are, both of them will be cancelled out from numerator and denominators. Alright, so if we do this integration, it will be 0 to EF e to the power 3 by 2 dE divided by integration from 0 to EF e to the power 1 by 2 dE. That will be equals to this will be 2 by 5 EF to the power 5 by 2 divided by 3 by 2 2 by 3 EF to the power 3 by 2. Alright, and that gives you your average energy E as 3 by 5 EF to the EF. Okay, and yeah, I guess in the lecture this has been shown. It is basically your total energy divided by the number of particles. Okay, and that has been calculated because those calculations were done at 0 Kelvin, and here we can see that. So the general formula is this actually. So finding the at any temperature, if you want to find the average energy, the general formula is this. Alright, and since we are talking about 0 Kelvin, we see that the Fermi-Dirac distribution will be 1 for energy less than EF, and it will be 0. So then F of E will be gone, and if you do this integration, then you will come back to the same result that you have derived in the lecture as well. So this is the average energy of the electrons at T equals to 0 Kelvin. Now the other thing is the energy of a classical free particle at temperature T is given by, so this is the what we have asked is, if we have a classical particle, then that classical particle at some temperature T, it will have average energy as 3 by 2 kBT. Okay, so now we want to find the temperature at which this classical energy will be equals to the this average energy of the electrons. So we need to equate both of them. So that will be equal 3 by 2 kBT times what we have is the average energy is 3 by 5 of EF. So from here T is going to be equals to 2 by 5 of EF upon KB, and EF upon KB could be written as TF. So basically T will be equals to the T that we need, which is the classical temperature. Okay, T that we have to find, and not the classical, basically the temperature at which this classical energy will be equals to the average energy of the electrons, that will be equals to 2 by 5 times of the Fermi temperature TF, and TF is your Fermi temperature. Right. So from here, okay, so here EF is given to us. EF is equals to 5.51 electron volt. Okay, alright. So TF will be equals to EF upon KB, which will be 5.51 divided by 8.6173 into 10 to the power minus 5. Okay, and that will give you a TF value of 6.39 into 10 to the power 4 Kelvin, right? And so the main two things that we have to find. So the average energy E, that is given by 3 by 5 times of EF. So that will come as 3.306 EV. Alright, and the temperature T at which the classical energy is going to be equals to this average energy that we have seen, that is going to be 2 by 5 times of TF, and that will be equals to 2.556 into 10 to the power 4 Kelvin. 2 by 5 times of this TF. Okay, so this was our this problem number 4. Let's move on to problem number 5. Okay, so problem number 5, so this is the problem from Jaskitter book, solid state physics. Okay, so in this problem what is asked is we have to find the pressure and bulk modulus of an electron gas. So first the problem is derive a relation connecting the pressure and volume of an electron gas. Okay, pressure and volume of an electron gas at 0 Kelvin. Okay, now it is same day using the result from problem. So the problem 1 we have solved in our last session. So in our last session we have solved that the kinetic energy of a 3D gas of n free electron, this will come as, so this relation, this we have done in last week. This is the week 1. Okay, so if you go to week 1 lecture, so in week 1 we have derived this relation that the kinetic energy of a 3D free electron gas at T equals to 0 Kelvin, that is going to be 3 by 5 times of n epsilon f, and using this relation now we have to find a relation that will connect the pressure and volume of the electron gas. Okay, and it also said that the relation actually is going to be this 2 by 3 times of U naught V. And then in the B part we have to show that the bulk modulus, which is defined as this, correct, which is defined as B is equals to minus V del P upon del V of an electron gas at 0 Kelvin. That is given by this radiation, next radiation, and then we have to estimate using the value that is for potassium. It is given the experimental value of Burke modulus of potassium is given to us. So we have to find the electron gas contribution to this Burke modulus. Alright, so this is our problem. So okay, now in general the pressure P is given by minus del U by del V at constant entropy. So this comes from thermodynamics. So for now, let us take it for like given, like that, like this is also given to you. But pressure is basically given by minus del U by del V at constant entropy if your entropy is constant, and at absolute zero, okay, which is T equals to 0 Kelvin, at which we are doing this calculation. All processes are at constant entropy. So this is by the third law of thermodynamics. The third law of thermodynamics. Right. So by the third law of thermodynamics, this entropy for all the processes will be constant entropy, and then we can just write the pressure as minus del U by del V, okay, where U is our energy of our system, and in this case energy we are just talking about free electron gas, so that is just equals to the kinetic energy of this 3D electron gas. Alright, so what we have is our pressure could be written as minus del U naught by del V, where U naught is given as 3 by 5 times N times epsilon F. Alright, so we can calculate pressure using this formula. We don't have to think about entropy here. Now U naught, now we need to find what is the relation between U naught and V first. So that will be given by 3 by 5 times of capital N. And now this is the Fermi energy. So Fermi energy will be equal to h by kf square by 2m. Alright, and then we know a relation between kf and the electron density. So this will be equal to 3 by 5 times n, hy square by 2m, and kf could be written as 3 pi square times electron density, could be written as n by v to the power. Okay, so we know that kf is equals to, since kf is equals to 3 pi square n to the power 1 by 3. Alright, so this we know, so that is what I have used here. So because of this U naught, now everything else, so we are taking differentiation with respect to V, so everything else will be a constant. So you can just take everything as some constant C. So U naught could be written as C times this V to the power minus 2 by 3, where this where this C is equals to 3 by 5 times 3 pi square to the power 2 by 3 hy square by 2m n to the power 5 by 3. Okay, so but this is just a constant. So our pressure P and U naught given by C V to the minus 2 by 3 is minus del U by del V, del U naught by del V, that equals to C. It will be d V to the power, we have minus 2 by 3 by dV. Alright, so if we do this integration, do this differentiation, we get 2 by 3 times of C V to the power minus 2 by 3 and a V to the minus 1. Right, so I am writing it in this form because you can see that C times V to the power minus 2 by 3 is again going to be U naught. So our pressure P will be equals to 2 by 3 times this will be equals to U naught times V inverse, or I can write it as pressure will be equals to, basically pressure is equals to 2 by 3 U naught by V. Okay, so this is the relation, and this is the relation what is given in the problem as well. So this relation we have found. This was our part A. Now for part B, okay, let me write it as this is part A actually. So this is part A we have solved. Right, now part B. Now part B we have to find the bulk modulus, and for bulk modulus we know the formula is minus V del P upon del V. That will give you the bulk modulus. So that gives you minus V del by del V of, we have 2 by 3 U naught by V. Right, and U naught also actually U naught also depends on V here. So what we have is minus V del by del V 2 by 3 C times V to the power minus 2 by 3 by V. Right, so I will have we have minus 2 by 3 C V d by dV. Okay, I can just write it as d by dV now. V to the power minus 2 by 3 minus 1 minus 5 by 3. Alright, so if you do the differentiation here, this will be minus 2 by 3 and we will have a minus 5 by 3 from differentiation. CV V to the power, I will have minus 5 by 3 and minus 1, you can write it as minus 8 by 3, or just leave it at minus 5 by 3 V to the power minus 1 again. And again what we have is 10 upon 10 by 9, and again C times V to the power minus 2 by 3, C times V to the power minus 2 by 3, yeah, I will take from here. So C V to the power minus 2 by 3, I will take V and V inverse will just cancel out. Okay, this V and this V. Okay, this two will just cancel out. Okay, V and V inverse, and I will take minus 2 by 3 from here, so I will have a V inverse remaining. Alright, and this will become U naught. So our bulk modulus T will come as 10 by 9 times, and this is equal to U naught. U naught by V. Alright, okay. So this is our bulk modulus, and this is the relation that is given in the problem as well. So bulk modulus comes at 10 by 9 U naught by V, and then okay, and also this could be written as, since we know that pressure is equals to 2 by 3 times of U naught by V, I can also write it as 5 by 3 of P. Yeah, because since P is equals to 2 by 3 of U naught by V. Okay, P is equals to, we have divided 2 by 3 of U naught by V. So that's why we can write it as 5 by 3 times of PSV. Alright, so this was part B, and then let's move on to part C. Okay, so let's move on to part C, and part C is we have to estimate for potassium using table 1 the value of the electron gas. Okay, we have to find the value of the electron gas contribution to B in case of potassium. And for potassium, what are the things are given to us? We are given the experimental bulk modulus is given to us, and for potassium the electron density, the Fermi energy, that is also given to us. Okay, and in different units. Okay, it is given in 2.12 electron volt, and then we can change this into ERG, and then 1 ERG per centimeter will be equal to 1 dyne, and 1 Pascal will be equal to this. Right, and so these things we are going to use. Okay, and because the experimental value that is given to us in what unit? In gigapascal. Alright, so first of all, this bulk modulus B, what we have derived is 10 by 9 times U naught by V. Now this could be written as 10 by 9. We have 1 by v, and then u naught we know that we have derived in the previous lecture 3 by 5 times n epsilon f. Okay, and this is given as well. The average kinetic energy is basically 3 by 5 times of n times of epsilon f, which is the Fermi energy. Okay, so this we have. So from here we can write our bulk modulus as 3 and this will cut, it will be 2 by 3 times electron density. So n by v will be equals to electron density times the Fermi energy. Okay, so this is the formula that we have. Now for potassium, n is given to us, which is 1.4 into 10 to the power 22 per centimeter cube. Okay, so this is the value. Okay, so the n value is given in per centimeter cube, so that we need to check. It is given in per centimeter cube. Right, so it is 1.4 10 to the power 22 per centimeter cube is given, and the Fermi energy is given as 2.12 electron volt. So our bulk modulus, so that is going to be equals to, it will be 2 by 3 times the electron density, which is 1.4 into 10 to the power 22 per centimeter cube, times the Fermi energy, which is 2.12 electron volt. And now since it is given in per centimeter cube, and it is given to you that 1 electron volt is equals to 1.6 into 10 to the power minus 12 ERG. Okay, so it means, so I will convert this value into ERG. So it will be, I will multiply it by 1.6 into 10 to the power minus 12 ERG per electron volt. Okay, so so you can see that the dimension, so the bulk modulus now, if you do the calculation, and this electron volt units will cancel out, and our answer will be in ERG per centimeter cube. So we have 3.16 into 10 to the power 10 ERG per centimeter cube, and ERG centimeter inverse is equals to dyne. So this bulk modulus will come as 3.16 into 10 to the power 10 dyne per centimeter square. Okay, so I can write it in dyne per centimeter square, but I have to compare it with the experimental value, which is given in Pascal, and 1 dyne, and this is also given to you that 1 Pascal is equals to 10 dyne per centimeter square. It means our bulk modulus in Pascal will be given as 3.16 into 10 to the power 9 Pascal. Okay, because since 1 Pascal is equals to 10 dyne centimeter square. Okay, and here 1 ERG centimeter inverse is equals to 1 dyne. Alright, square. So this will be our okay, and 10 to the power 9 is basically gigapascal, so P could be basically written as 3.16 gigapascal. So this is our bulk modulus for the potassium, if we consider this free electron gas model. And here you can see that the experimental value of the bulk modulus of potassium, that is also 3.1 gigapascal. So we can see that this Drude model works quite well for this this free electron gas model. It works quite well for the case of potassium matter. Okay, the bulk modulus value, whatever the electronic gas contribution is, just considering free electron gas, the bulk modulus that we have calculated, which is 3.16 gigapascal, it is very extremely, you can say, like very close to the experimental value, which is 3.1 gigapascal. Alright, so let's move on to our next problem number 6. Alright, so in problem number 6 we have to find the frequency frequency dependence of the electrical conductivity. This is also from Charles-Kittel. So use the equation, we have to use this equation, m dv by dt plus v tau is equals to minus E times electric field, which is basically our general force equation. Is general equation of motion that we had. If you remember, like force, basically what dp vector by dt is basically dp vector by dt is equals to minus E times E divided by M, right? Sorry, sorry, dp vector by dt is minus E times E minus P vector by tau, correct? So that is given in this form here, in the form of velocity. For the electron drift velocity, okay, it is the electron drift velocity v. To show that the conductivity at frequency omega is given as this, where sigma naught is our DC conductivity and E square tau by m. Okay, so let the electric field E is given by E naught times e to the power minus iota omega t, and this drift velocity v is given as v naught e to the power minus iota omega t. So E naught and v naught are your the electric field and the drift velocity in case of DC, if you have like DC conductivity, then when there is no frequency dependence. Okay, now they are just a magnitude. Okay. Then what we have, I am writing so we are writing it in form of this velocity dv by dt plus v by tau. This could be written as minus E by m. Alright, and then if we do the differentiation, then it will come as v naught minus iota omega e to the power minus iota omega t plus whatever our v is divided by tau equals to minus E naught, okay, minus E times E actually. Okay, so this will remain the same. Okay, so I have written it in this. Okay, so it will be this, and this v naught times e to the power minus iota omega t, this can again be written as v tau is equals to minus E times E. So I will take v common here. We have 1 by tau minus iota, or if you write it properly, so we will have tau is equals to 1 minus iota omega tau, that is equals to minus E times E. So v will be equals to minus E. Okay, so it is E minus E by m minus E by m, minus E by m divided by 1 minus iota omega tau divided by tau. Okay, let me just keep it in this form for now. Okay, 1 by tau minus iota omega. So I will write it as 1 by tau minus iota omega. Okay, so this is my velocity minus E by m, 1 by tau minus divided by 1 by tau minus iota omega. Now we know our current density J, and it is written as minus NeV. Alright, this we know. Okay, the electron density times the electronic charge times whatever the drift speed is. Okay, so from there I can write J, and I have this formula of V. So whatever I have, E by m divided by 1 by tau minus iota omega. Alright, so J will be equals to N E square by m times, this will be now, okay, 1 minus iota omega tau times the electric field E. Now I will write it as N E square tau by m, right? I will write it 1 minus iota omega tau, and I will multiply it by 1 plus iota omega tau, 1 plus iota omega tau times the electric field. Okay, that is just multiplying by 1. Now here this is our sigma naught. Okay, this is our for DC conductivity N E square tau by m. Alright, this is our sigma naught. So J will be equal to sigma 0 and 1 plus iota omega tau, this is tau divided by 1 plus omega square tau square. Okay, by multiplying this 1 minus iota omega tau times 1 plus iota omega tau times the electric field T. So this will be equal to our J of omega basically equals to, so this we can see that this is going to be our conductivity, sigma omega, because we know that g of omega will be equals to some sigma omega times e of omega. So that from here our electrical conductivity, frequency dependency of this electrical conductivity, that comes as sigma 0 times 1 plus iota omega tau divided by 1 plus omega square tau square. Okay, so this is our answer. So this is what we have to do. Let me just check. Alright. Okay, so this is what we have to do. Right. Sigma 0, 1 plus iota omega tau, 1 plus omega tau whole square. Okay, you can write it as omega tau whole square. Omega square tau square will be written as omega tau whole square. Alright, so this was our problem number 6. Let's go to problem number 7. Okay, so problem number 7 is this is a numerical problem. So let's say we have a copper wire at room temperature 300 Kelvin, and it has a thermal conductivity is given to us 400 watt per meter Kelvin, and given the Lorentz number for copper is given to us 2.44 × 10⁻⁸ watt ohm Kelvin square. Determine the electrical conductivity for copper at room temperature. So we have to determine the electrical conductivity. So for this, this is a simple problem of the Wiedemann-Franz law. So the Wiedemann Franz law states that, so this is our Lorentz number L. So our Lorentz number L is given by K divided this kappa divided by sigma tau, sigma t, okay, where this so where L is our Lorentz number, okay, and this is given to us as 2.44 into 10 to the power minus 8 watt omega Kelvin Kelvin to the power minus 2. Then we have this kappa, which is our thermal conductivity, which is given as 400 watt meter inverse Kelvin inverse, T here is our absolute temperature. Yeah, this is also important. So absolute temperature means the temperature is in the units of Kelvin. So whenever you solve the problem, it's better to convert your temperature to Kelvin scale, convert your temperature to the absolute temperature. So temperature is given in degree centigrade or something, and convert it into Kelvin. Here it is given in Kelvin, 300 Kelvin. Okay, and the last thing is our electrical conductivity. Which has a unit of Siemens per meter. Okay, so Siemens is basically we know that the unit of resistivity is ohm. So ohm inverse is Siemens. So this so you might get in your problem, like here we have to find the electrical conductivity, and some problem you might get electrical conductivity in the unit of this unit Siemens per meter. So Siemens is just your ohm inverse. So it is the SI unit. Right, and from there, now from this Wiedemann-Franz law, we can write sigma is equals to kappa divided by L in times T. Alright, and we have our so we have kappa is basically 400 watt meter inverse Kelvin inverse, Lorentz number is 2.44 into 10 to the power minus 8 watt omega Kelvin to the power minus 2, and we have 300 Kelvin. So here you can see that you can check that the dimension, you can take that, do the dimensional analysis. Kelvin, the Kelvins will cancel out, watt will cancel out, and whatever remains will be ohm inverse and meter inverse, and ohm inverse will be in is Siemens. So if you calculate it, you will get 5.46 into 10 to the power 7 Siemens per meter. Right. So that is how we can calculate our electroconductivity using Wiedemann's formula. Alright. So mainly you have to remember this formula. The Lorentz number is equals to kappa divided by sigma t. Okay, let's go to problem number 8. So in problem number 8, what is given to us? So this is a problem on Hall effect. So a copper strip of 2 cm wide and 1 mm thick is placed in a magnetic field B, which is equals to 1.5 Weber, and Weber is basically this must be Weber per something. Okay, let me just check. This is okay. You have to check. Just 1 minute. This is Weber. Just like this. Per square meter. Alright, so sorry about that. This is Weber per square meter. So per square meter will be there. Yeah, I have to correct it. It is wrong. It will be meter to the power minus 2. Okay, it will be meter. So basically, 1 Weber meter square is equals to 1 Tesla. Alright. So so the magnetic field could be given in units of Tesla. Okay, it is generally given in units of Tesla, but sometimes it might be given in units of the other SI unit is Weber per square meter. Okay, so 1 Weber per square meter is equals to 1 Tesla. I forgot to put the meter square here. Sorry about that. So magnetic field is given to us 1.5 Weber per meter square, or which will be basically 1.5 Tesla. And if a current of 200 ampere is set up in the strip, calculate the whole voltage that appears across strip. Okay, so we have to calculate the whole voltage. Alright, so for this, let me first draw the for the revision. Let me just first draw the setup what we have here. So what we have is okay. So we have our sample. Okay, and in this we are providing it with, we are giving it some current I. Okay, and the magnetic field is being okay. So this is your normal Hall effect setup. So okay, so you have a magnetic field in the vertical direction. The thickness is given as to us as T. Okay, so let's say this is your thickness T. This is your width. Okay, this is width and this is your thickness T. Okay, so what is given is how, like if you in the question it is given that it is this wide and this thick, it means those are this dimension. When you are saying wide, mostly it is this one which is perpendicular to your magnetic field, and thickness is the thickness of the sample which is parallel to the magnetic field. And then this is Ex, the electric field, and this will be Eh. So basically, as you know, because of this Lorentz force, because of the magnetic field, the electrons will move in the y direction. So let's say this is your x direction, this is your y direction, and this will be your z direction. So your electrons will move in the y direction, and because of this electric field, a voltage will get developed, which is the whole voltage that we have to calculate, and correspondingly there will be an electric field as well. Okay, this is the Hall field, you can see. So here we have B is our magnetic field. I is our current, T is the thickness of sample along the magnetic field, and W is the width of the sample along all field developed, and J is our current density. So okay, and as we know, so this Jx, okay, so we have the current is flowing in the x direction, so your this current density Jx, if I take current density Jx, will be equal to whatever the current is divided by W times T, whatever the cross section area. So the cross section area for this current will be W times T, which is flowing in the x direction. Okay, so this is the cross section area which is shaded. Okay, so it will be I divided by WT. So okay, and VH is our whole voltage that we have to find. Now this okay, so these are the lines. So let me just start writing in black now. So what we have to find? We have to find the whole voltage. Okay, and these are all the things that is given to us. And the whole voltage we know will be equals to EH times W. Okay, so that comes from like electric field. Basically, if you remember, an electric field E is equals to minus del V by del X. Alright, so whatever the potential difference is, and that is what is our whole voltage is, and the separation is W here. Okay, so you can see that this this is going to be this is going to be our VH. Okay, okay, this will be the potential. So this potential difference is going to be VH. Right, if I put a voltmeter here, so this will be our this is going to be our whole voltage, and this separate this length is W, so that's why our whole voltage could be written as EH times W. Okay, is EH times W, and then what is given to us is a whole coefficient RH is given to us, and RH, okay, this is our whole coefficient. Now this we know is given by EH. It is given by EY, which was basically the electric field in the y direction. If your current is in the x direction, the voltage, the electric field in your y direction, which is EH, we have written it as EH. So it will be EH divided by JX and B. Alright. So from here, our EH will be equals to JX will be equals to RH JX times B. So your whole voltage that you have to calculate, that whole voltage will be equals to EH times W. So that will be equals to RH JX B times W. Alright. So from here I can write VH is RH. Now JX I can write as I upon WT. Okay. And I have B times W. Here I can, okay, so I can cancel out this WW. So VH will be equals to RHIB by T. So this is the formula for our core voltage, RHIB by T. And then you just have to put in the values. So VH will be equals to, so this is given as 1 point, and this is given as 6 into 10 to the power minus 7 meter cube. This is the RH, yeah. Per coulomb. Okay, so this is coulomb per coulomb. It is given as 200 ampere. SI units we have 1.5 Tesla, and we have 1 into 10 to the power minus 3 meter. Alright. So if you do this calculation, and everything is in SI units here, so your voltage will also be in SI units if you just do the calculation, and it will be 0.18 volt. Okay, so this is our whole voltage that we have to calculate. Alright, so this was our problem number 8. Okay, so let's now solve some problems from our previous session from week 1. Right. So from week 1, we briefly discussed this problem because we didn't have time in the last session. So let's just solve this now. So we have to. So this is a problem again from the Kitter, and this is the Fermi gases in astrophysics. So let's say we are given that m naught is our mass of the sun. It is given in grams, 2 into 10 to the power 33 gram, and we have to estimate the number of electrons in the sun first. Okay, what are going to be the number of electrons? And in a white dwarf, and what is given as in a white dwarf star, this number of electrons may be ionized and contained in a sphere of radius 2 into 10 to the power 9 centimeter. Find the Fermi energy of the electrons in electron volts. Okay, so first we have to find the number of electrons in the sun, and then what it is asking is that consider that you have a sphere. So in white dwarf we can consider that it is a sphere. All these electrons will be ionized. So basically we have these free electrons in a sphere of radius 2 into 10 to the power 9 centimeter, and then we have to find the Fermi energy. Alright, so first of all what we can say is that mass of a nucleon, which is either a proton or neutron, that is approximately equals to 1.7 into 10 to the power minus 24 grams. Right, so we can approximately the size of a proton and neutron, they are similar, so we can approximate them to be 1.7 10 to the power minus 24 gram. And in the sun the number of nucleons, okay, so in the sun, now you can assume that since we know that is the electrons are very light compared to these protons and neutrons, so we can consider that the mass of the sun that is given to us, that is approximately because of these protons and neutrons only, because of nucleons only. So using that assumption, in the sun the number of nucleons is given by the mass of the sun. So we are just mass of the sun divided by mass of a nucleon. Assume mass of sun comes from nucleons only. Okay, so we are considering that the electrons are quite light. They are 10 to the power minus 31 in kg. So in gram they will be like 10 to the power minus 34 grams. So they are like 10 to the power minus 10 times lighter than this nucleon. So we can assume that whatever the mass of the sun that is given, that is mostly because of this nucleon only. So nucleon, which will be your proton, and if you consider like it is all made up of hydrogen, then okay, so that is just so we can just consider that it is mass of all the whatever the protons and neutrons are there. So from there we can find the total number of nucleons, and 10 to the power 33 gram. So the mass of the sun is 2 into 10 to the power 23 gram, and mass of a nucleon is 1.7 into 10 to the power minus 24 gram. From there this number comes as 10 to the power 57 nucleons. Okay, so we can assume that we have 10 to the power 57 number of nucleons, and then and also like we can assume that there are roughly equal number of electrons and nucleons. Okay, so we are assuming that there are equal number of electrons and nucleons. Okay, assuming, okay, and I have taken this mass as given. No, it's not as given. Yeah, so assuming only, let's say, hydrogen atom, 1H1 in the sun. Okay, so let's just assume that whatever the sun is made up of, it is mostly made up of hydrogen only. Okay, so so basically, so if we first find that, you can say we first find the total number of protons, and in hydrogen there is one proton and one electron, so there will be roughly equal number of, you can say, there will be equal number of these protons and neutrons, electrons. Alright, so if they are 10 to the power number 57 nucleons, so it means 10 to the power number 57 protons, so there will be 10 to the power 57 number of electrons as well. So number of electrons in the sun, therefore number of electrons, okay, this is again in part A, right? In part A we have to find the number of electrons and then the Fermi energy. So we can say the number of electrons in the sun, which is n, I'm denoting it at n, that is also I can write it at 10 to the power 57. Okay, so this is our total number of electrons here. Now in a white dwarf, star of volume V, volume V, where V is equals to 4 by 3 pi, R is given as 2 into 10 to the power 9 centimeter per cube. So this volume will be approximately equals to 3 into 10 to the power 28 centimeter cube. Alright, so this is the volume that is given to us. So from here, so basically we are putting all those electrons within this white dwarf, this big, which has a volume this, so this big sphere. So the electron concentration n, small n, is given by, so small n will be equals to capital N by V, which will be equals to, we have 10 to the power 57 number of electrons times divided by the volume, it is 10 to the power 28 centimeter cube. So our n will come as approximately, we will write it as 3 into 10 to the power 28 per centimeter cube. Okay, so this will be our electron density. Thus Fermi energy, epsilon F, is given by, so we know this formula, epsilon F for the free electron gas, 3 pi square n whole to the power 1 by 3. So we just have to use this formula. Sorry, is given, sorry, so this is kf. Okay, we know this is the Fermi vector. Okay, this is the Fermi vector. Okay, this is the Fermi vector. Fermi vector is given by kf is 3 pi square n whole to the power 1 by 3. So our epsilon F energy, Fermi energy, we have to calculate. That will be equals to h pi square kf square by 2m. So it will be h pi square by 2m, 3 pi square n whole to the power 2 by 3. Just finding it. Yes. Right. 3 pi square n whole to the power 1 by n, and here this m is the mass of electron. Okay. This is the mass of electron. Alright. H pi is your reduced Planck constant, which is 1.05 into 10 to the power minus 27 in ERG second, and you remember 1 ERG is equals to 10 to the power minus 7 joule, and 1 electron volt is equals to 1.6 into 10 over minus 19 joule, right? So from here I can write my EF as, okay, just put in this value. So which will be if I take the Planck constant in this unit of ERG second, because basically I am using n in per centimeter cube, so only that's why I am taking this into power minus 27 whole square times 3 pi square times 3 times 10 to the power 28 2 by 3 divided by 2 times mass. Second, ERG second, and 1 ERG okay, okay, let's correct 1 ERG 10 power minus 7 joule. So let me just write the units here. So it is ERG second whole square 1.05 into 10 to the power minus 27 ERG second whole square, right? It is our h5 square, and then we have 3 pi square n is 3 into 10 to the power what we have calculated 10 to the power 3 into 10 to the power 28 per centimeter cube whole to the power 2 by 3 times divided by the mass of the electron, okay, which is 9.1 into 10 to the power minus 28. Sorry, yeah, it is 10 to the power minus 31 kg, so it will be 10 to the power minus 28 in grams. So that will be in gram. Alright, so if you calculate it, the second one. Okay, so if you calculate this, EF comes as here the second, I have a gram and gram per, here from here you have gram centimeter gram to the power minus 3 times 2 by 3 gram per centimeter square. Okay, basically you have unit of gram per centimeter square and per centimeter square, and okay, so yeah, so the unit that you just check, because it will be gram per centimeter square plus second square, okay, and that will come to be the unit of ERG, so there will be just one ERG here, okay. So I was just taking the this dimensional analysis, so there will be ERG square here, and there will be gram per centimeter square gram, and there will be per centimeter square. So this will come down gram centimeter square per second square. So that will be equals to ERG. And so when ERG we cancel out. So your answer when you solve it, your EF approximately comes as 5.6 into 10 to the power minus 8 ERG. Right, in the energy unit, and then we can convert it into joule. 5.6 into 10 to the power minus 15 joule, which will be converted to if you convert it into electron volt, it will be 3.5 into 10 to the power 4 electron volt. So this will be our Fermi energy, 3.5 into 10 to the power 4 eV. Right. So this is our Fermi energy. Then for the B part, let's go to the B part now. Okay, so this I hope this is clear. Okay, so I was just confused about the dimensions. Dimension are here, but that is correct. There will be gram, and the centimeter square will come down, and there will be per second square, and that will be ERG. Alright. Then in the B part is also the energy of an electron in the relativistic limit. Okay, the energy of an electron in the relativistic limit, where the energy is much greater than the mc square value, is related to the wave vector as this. Okay, so it is saying that, okay, so basically what you are saying that instead of rating your energy, electron's energy as h5 square k square by 2m, your energy relation, energy dispersion with respect to your k vector, that is now given as a linear. Basically you have a linear dispersion, that energy is equals to h5 k times c. Show that the Fermi energy in this limit is epsilon f. So we have to show that the Fermi energy, if we consider this limit, basically if we consider this relation, then epsilon f is given by this formula. The Fermi energy is given by this. Now from here, the value of kf is not affected by relativity and is approximately at n to the power value. Okay, where n is the electron concentration. Alright, so basically what I'm saying is that what we are changing here is the relation between the how energy depends on your wave vector k. So your dispersion relation of your energy, that has been changed. So instead of having it a parabola h1 square k square by 2m, what we are now saying is that it is linear. Okay, it is now some h bar times k times c, which is the speed of light. Alright, but your k will not change. So but your kf, the Fermi vector, that is not affected, so that will not change. Thus epsilon f will be just equals to, so you have your dispersion relation. Earlier you have h1 square k square by 2m. So if Fermi vector is given to you, then the Fermi energy was h5 square k square by 2m. Now the dispersion relation is just changed to linear, which is so it will be just h5 square c times kf. The Fermi energy is h bar times c times kf. So which will be approximately equals to, I can write it as h bar c n to the power 1 by 3. So we are ignoring those 3 pi square terms. So we can write our Fermi energy approximately. So our Fermi energy could be approximately written as h bar c n by v whole to the power 1 by 3. Alright. So this is our our Fermi energy will be given now. Okay, so let's go to the part C. Right. So in part C it is given that if the above number of electrons were contained within so this is the part C. So if the above number of electrons were contained within a pulsar of radius 10 km, show that the Fermi energy would be approximated and to power 8 electron volt. So basically now it is saying that basically it is just saying that you have a radius now of 10 kilometer. You have a pulsar of radius 10 kilometer. So you can consider that it's a sphere of radius 10 kilometer. And now it is asking what it is saying that you have to show that the Fermi energy is 10 to the power 8 electron volt. And there is then some explanation here. So this you can read on your own, this part. We can read afterwards. Alright, so let us solve this numerical problem first. So we need to find the Fermi energy. So change of radius. So we have basically a change of radius. Change of radius now to 10 kilometer, which is equals to 10 to the power 6 centimeter, makes the volume approximately 4 into 10 to the power. So that is just like we have calculated in part A. We have calculated the volume 4 by 3 pi r cube. So we have just changed the radius to 10 to the power 6 centimeter now. So our volume will become 4 into 10 to the power 18 centimeter cube, and the electron concentration that will become, which is n, will approximately equals to 3 into 10 to the power 38 per centimeter cube. Alright, so our electron concentration is changed, and thus EF value, okay, you have to use this formula, HY square by 2m kf square, and we know HY square by 2m will be equals to 3 pi square n whole to the power 1 by 3. So it will be whole to the power 2 by 3. Okay, this is the same thing we have done in part A. So you just have to change your value of n there, and what we will get is our EF will be approximately equals to 2 into 10 to the power minus 4 ERG. Alright, and which will be approximately equals to 10 to the power 8 electron volt. Okay, so this will be 10 to the power 8 electron volt. Right. So this is what you have to calculate, and then there is given the 2s that, okay, and that's what we have to prove, like the energy will be of the order 10 to the power 8 electron volt. Now this value explains why pulsars are believed to be composed largely of neutrons rather than of proton and electrons, for the energy released in the reaction changing neutrons to proton and electron is only 0.8 to the power 6 electron, which is not large enough to enable many electrons to form a Fermi C. Okay, so basically if you have a pulsar and you want to fill that pulsar with free electron, so we find that the Fermi energy that that electron density will correspond to, it should be around 10 to the power 8 electron volt, while it is said here that the energy that is released and making this free electrons, that is only around 0.8 into 10 to the power 6 electron volt. Alright, so which is not large enough to enable these electrons to form a Fermi C. So thus the neutron decay proceeds only until the electron concentration builds up enough to create a Fermi level. Okay, so the neutron decay proceeds only until the electron concentration builds up enough to create this, at which point the neutron, proton, and electron concentrations are in equilibrium. So basically, since the neutron decay, it will proceed until the electron concentration builds up enough to create a Fermi level. So only for the Fermi level of 0.8 to the power 6, only this neutron decay will proceed, and afterwards there will be equilibrium. So we cannot reach this higher value of 10 to the power 8 electron volt, and that's why it is believed that they are mainly composed of neutrons only, because that decay will not happen. So that is not the important part. So the main part was just that we have just changed the radius, we have changed the volume, and if we have changed the volume, we have changed the electron concentration, and then we just have to calculate our Fermi energy for the new concentration. Alright, so let's solve the last problem of this session, of today's session. So this is also from NPTEL. So what is given to us is that we have this is regarding liquid helium-3. So we have an atom helium-3, and let's assume that the helium-3 has a spin half. Okay, we assume that the the helium-3 atom, it has a spin half and it's a fermion. Okay, So helium-3 atom, it is a fermion. The density of liquid helium-3 is density is given to us of liquid helium-3 near absolute zero. Okay, at T equals to 0 Kelvin, it is given to us. We have to calculate the Fermi energy and the Fermi temperature Tf. Okay, so these are the two things we have to find. First is the number of moles per centimeter cube is, okay, so number of moles of helium-3 atoms. So basically what we have to do, we have to just consider our helium-3 as we have done the calculation for the free electron gas. We will just replace our electron with this helium-3 atom, and since it is cylinder, it is also spin half and also it is also fermion. So we will just consider that whatever we have derived for our free electron gas, that could be applied here as well. Alright, so the number of moles of helium-3 per centimeter cube is, so that will be, so density is given to us, which is 81 gram, 81 into 10 to the power minus 3 gram per centimeter cube. Alright, divided by, so we know the for helium-3 the atomic mass number will be 3. So you just divide it by 3. So that gives you 27 into 10 to the power minus 3. Okay, this will be the number of moles per centimeter cube. So the concentration of helium-3 is, so the concentration will be equals to for moles, so you just have to multiply by the Avogadro number, okay, 6.023 into 10 to the power 23, 27 into 10 to the power minus 3 times the Avogadro number, 27 into 10 to the power minus 3 times 6.023 into 10 to the power 23. Alright, if you do this calculation, it will be 16 into 10 to the power, approximately, you can say, I guess, it will be approximate, 16 into 10 to the power 21 atoms per centimeter cube. Okay, so this will be our, like we have the electron concentration, now we have this atom concentration. That's the same thing. And it is given that the mass of an atom of helium-3 is 5.01 into, okay, so we have the mass of electron, now we have the mass of this helium-3 atom, 5.01 into 10 to the power minus 24 gram, and again reduced Planck constant is given to us 1.05 into 10 to the power minus 27 ERG second. And again the same thing, 1 ERG is equals to 10 to the power minus 7 joule, and 1 EV is equals to 1.6 into 10 to the power minus 19 joule. Right. So we have to calculate the Fermi energy. Now the Fermi energy it is given as h1 square by 2m. Alright, and here kf is equals to 3 pi square n whole to the power 1 by 3. Alright, so our Fermi energy EF will be equals to h pi square by 2m pi square n whole to the power 2 by 3. Now this we can approximate to, again just put in the values, 1.05 into 10 to the power minus 27 whole square times 3 pi square to the power 2 by 3 times this, instead of electron density we just have the helium-3 density in the power 21 into power 2 by 3 divided by 2 into whatever the mass is, 5.01 into 10 to the power minus 24. Okay, this is given in grams. Okay, and if we do the calculation as we have done earlier in the previous one as well, you get 7 to the power minus 16 ERG, and if we do the if we convert it into joule, then this value comes as, and the answer joule only, 7 into 10 to the power minus 23 joule. Okay, so this is the answer. This is what is asked, right? Okay, yeah, we have to find the Fermi energy and the Fermi temperature as well. We have to find the Fermi temperature as well. Okay, and then using like TF is equals to epsilon F upon KB. Okay, and KB is our Boltzmann constant. KB, I am using the value 1.38 into 10 to the power minus 23 joule per Kelvin. So your TF will come as 7 into 10 to the power minus 23, it is joule, divided by 1.38 into 10 to the power minus 23 joule per Kelvin. Is Kelvin inverse. So if you do the calculation, your TF will come as approximately 5 Kelvin. Okay, so this is interesting. So like if we are considering, instead of electrons we are considering this helium 3 atoms, then our TF value is very small, it is like 5 Kelvin. Well, if you remember, for the electron case, this Fermi temperatures, they are like quite high. Okay, because the Fermi energy is also quite high. Alright, so this one, but in this case also, in this case this is different. The TF value is small, like 5 Kelvin or something. Alright, so this was the last problem of this session. Okay, let me just stop sharing. Right, do you guys do you have any doubt in this session or in the previous session, or in general if you have any doubt? Okay, okay, assignments, let me check. Actually, we can't discuss the assignments in this session until the deadline is finished or not. That I have to check actually. That's the thing. So okay. Hmm. Hmm. I have to check here. Okay, so yeah, I guess they must be talking about. They must be. They might be taking the momentum to be momentum, or the change in momentum as same. Maybe in that question, they might have just okay. But like we can't. So let me just see the problem. Okay, you're saying problem number 5, I guess. Yeah. Using Heisenberg's uncertainty principle, the momentum decreases by half. Because of two bases, the two bases are pushed together to form a bigger box. Which of the following statement is not true? Yeah, I guess they are talking about, since they are talking like Heisenberg uncertainty principle, right? Most likely, yeah, they might be just taking this change in momentum and a momentum similar, maybe for this problem. I guess, yeah, the momentum decreases by half, so it seems like they are taking it to be, they are considering it in the same fashion, like the change in momentum. Okay, in the lecture we can discuss. Okay. Ah, jx by b. Yes, yes. G. Okay, yeah. Yeah. That I will check. Yeah, I was also you are right. Yeah. When we talk about, I guess, this like B, I guess we talk about in magnetic. Instead of field, I guess you talk about intense flux or something. I guess there, uh, in that conversion, something happens. I guess. Yeah. That I have to check what is given in the lecture, how the that one by c comes. One by c, you are right, actually there might be only in that case only mostly it comes, like if you have b and h thing happens. So yeah, 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 we'll check it, and we'll discuss in the next session, like why that one by c is coming. Okay. But generally when you hmm? Yeah, okay. So, is there any question in that assignment? Yeah, so in the assignment, so if the as we have solved in this session as well, if you have to solve the questions in the quiz or assignment of this Hall effect, you don't need that C value. You just have to use the RH equals to 1 by NE only. You don't need to use that C. You have to check how he has given, because generally you give the magnetic field only. So if you are using this magnetic field, then you just have to use the formula. The whole coefficient will be 1 upon NE only. You don't have to use C. Uh, uh, yeah, I'm also not sure, but yeah, I guess during my bachelor's I gave I did one NPTEL course during my bachelor's. So that time, yeah, I guess the calculator was allowed. Calculator, uh, you must be able to use the calculator in the exam, in the final examination, most likely. Most likely, but yeah, but it's better to confirm from the instructor, actually, because I guess, yeah, like I'm not sure, like the things change with the things might change with from instructor to instructor as well. So I'm also not sure. Okay. You can mail him, or maybe you can ask in the discussion of forum as well. Discussion for forum as well. You can just ask this query. So there also you can ask, or maybe email the professor, whichever works. But most likely, yeah. Uh, when I did one NPTEL course during my bachelor, so I did just one course, and in for that for that I went for the final examination. It was in Kanpur only, so that's why I gave. At that time, I used calculator in that examination. So most likely for this as well, there would not be any issues with using calculator. Okay. Okay. So so if there are no other doubts, then we can just uh, close this session. Okay. Thank you.